What if I told you that millions of years before humans ever walked this earth, another civilization might have risen, built cities, developed technology, and then vanished so completely that we'd never know they existed? What if the very ground beneath your feet holds secrets of a lost world that predates our entire understanding of history? This isn't the plot of some science fiction movie. This is a legitimate scientific hypothesis that's been keeping researchers awake at night, forcing them to question everything we think we know about our planet's past. It's called the Silurian Hypothesis, and it might just be the most unsettling question science has ever asked. The name comes from Doctor Who, believe it or not. In a 1970 episode, the Doctor encounters an ancient race of technologically advanced reptilian humanoids called the Silurians, who ruled Earth long before mammals ever evolved. These fictional beings went into hibernation underground to avoid a catastrophe, waiting millions of years before awakening to find their world overrun by upstart humans. But in 2018, two very real scientists decided to ask a very real question. What if something like this actually happened? What if there was a civilization that existed so long ago that almost all evidence of their existence has been ground to dust by the relentless march of geological time? The scientists behind this mind-bending hypothesis are Adam Frank, an astrophysicist from the University of Rochester, and Gavin Schmidt, a climate scientist and director of NASA's Goddard Institute for Space Studies. These aren't fringe theorists or conspiracy enthusiasts. These are serious researchers with impressive credentials who decided to explore one of the most provocative what-ifs in scientific history. Here's what sparked their collaboration. Frank was initially interested in detecting alien civilizations by looking for their impact on planetary climate through things like ice cores and tree rings. But then he had a chilling realization. If we're looking for signs of industrial civilizations on distant exoplanets, shouldn't we first figure out how to detect such signatures right here on Earth? That's when the truly unsettling question emerged. How would we even know if an advanced civilization existed on Earth before us? Not just a few thousand years ago, but millions of years ago, long before humans, long before most of the species we recognize today? The more they dug into this question, the more disturbing the answer became. We probably wouldn't know. In fact, we almost certainly wouldn't know. Think about it this way. Human industrial civilization has been around for maybe 300 years. That's not even a blink of an eye in geological terms. Our entire species, Homo sapiens, has only existed for about 300,000 years. Complex life on Earth's land surface has been around for roughly 400 million years. Those numbers should make you pause. We've had sophisticated technology for less than 1,000th of the time that complex life has existed on this planet. Now here's the kicker. What are the chances that in all those hundreds of millions of years, no other species ever developed technology? What are the odds that evolution never produced another intelligent species capable of building cities, harnessing energy, and reshaping their environment? When you put it that way, it starts to seem almost arrogant to assume we're the first. But that assumption is built into everything we think we know about Earth's history. The problem is that direct evidence of ancient civilizations would be incredibly hard to find. Fossilization is rare under the best circumstances. Most of Earth's exposed surface is younger than 2.5 million years old. The oldest surface on our planet, a stretch of Israel's Negev desert, is just over 1 million years old. That's nothing on a geological timescale. Even if dinosaurs had built mile-high cities and driven cars through bustling metropolises, all direct evidence of their civilization would have been ground to dust over tens of millions of years. Buildings would crumble, artifacts would decay, and tectonic activity would bury everything under new layers of rock or drag it to the bottom of the ocean. This creates a detection problem that's almost insurmountable. We're looking for a needle in a haystack, except the haystack is the size of a planet, and the needle might have rusted away millions of years ago. But Frank and Schmidt realized something crucial. While direct evidence might be impossible to find, indirect evidence might still exist. Instead of looking for artifacts or fossils, they started thinking about geochemical signatures. What would an industrial civilization leave behind in the chemical composition of ancient rocks? This is where things get really interesting and really unsettling, because the signatures they identified are exactly the kinds of changes we're making to our planet right now. An ancient industrial civilization would have needed energy. Lots of it. They would have burned fossil fuels, just like we do. This would leave behind distinctive carbon isotope ratios in the geological record. They would have mined metals, manufactured chemicals, and possibly even developed nuclear technology. All of these activities would leave chemical fingerprints that could theoretically survive for millions of years. The researchers identified several potential markers: rapid changes in temperature or climate, evidence of tapping geothermal power sources, anomalies in sediment composition like artificial fertilizers, unusual isotope ratios, plastics, and synthetic compounds that don't occur naturally, and even radioactive elements from nuclear technology. Here's the chilling part. These are the exact same signatures that human civilization is laying down right now. If future geologists were to examine rock layers from our era millions of years from now, they would find precisely these kinds of anomalies. But here's where it gets even more mind-bending. There's already a mysterious event in Earth's geological record that shows many of these exact signatures. It's called the Paleocene-Eocene Thermal Maximum, and it happened about 56 million years ago. During this event, global average temperatures rose by 5 to 8 degrees Celsius over a relatively short period. There was a massive input of carbon into the ocean and atmosphere. The chemical fingerprints look remarkably similar to what we would expect from large-scale industrial activity. Now, before you start planning your "I told you so" speech, the researchers are quick to point out that this event almost certainly wasn't caused by an ancient civilization. The carbon release happened over hundreds of thousands of years, while our current industrial spike has happened in just a few centuries. The leading explanation involves massive volcanic activity or the sudden release of methane from ocean sediments. But here's what's truly unsettling about the Paleocene-Eocene Thermal Maximum. It shows us exactly how industrial-scale environmental change would appear in the geological record. It provides a template for what we should be looking for, and this raises a terrifying possibility. What if there were other, shorter duration events that we simply haven't detected yet? What if there were civilizations that lasted only a few thousand years, leaving chemical signatures so brief that they're invisible to our current methods of geological investigation? Frank himself admits that if we wanted to look for evidence of a previous civilization, we would need to develop entirely new methods and examine the rock record on much finer timescales than we currently do. This brings us to one of the most disturbing paradoxes of the Silurian Hypothesis. The more advanced and sustainable a civilization becomes, the smaller the footprint it leaves on the planet. A truly advanced civilization might develop clean energy, sustainable manufacturing, and closed-loop resource cycles that leave almost no trace in the geological record. In other words, the civilizations most likely to survive for long periods would be precisely the ones we're least likely to detect. Meanwhile, civilizations like ours, which are rapidly altering planetary chemistry and driving mass extinctions, create obvious signatures but might not survive long enough to be considered truly successful. This detection paradox has profound implications, not just for understanding Earth's past, but for thinking about our own future. Are we destined to become one of those brief, violent spikes in the geological record? Or can we transition to a more sustainable path that might allow our civilization to persist for millions of years, even if future geologists struggle to detect our existence? The researchers also point out that spacefaring civilizations might leave more durable evidence on other worlds. The Moon and Mars lack the active geology that constantly resurfaces Earth. Ancient artifacts might survive much longer on these worlds, waiting for future explorers to discover them. But perhaps the most unsettling aspect of the Silurian hypothesis isn't what it tells us about the past. It's what it forces us to confront about the present and future. We're currently conducting a massive, uncontrolled experiment with our planet's climate and chemistry. We're laying down geological signatures that will be visible for millions of years. Future civilizations, whether human descendants or entirely different species, will be able to read the story of our era in the rocks. They'll see the rapid spike in carbon dioxide, the mass extinction event we're currently driving, the synthetic chemicals we've scattered across the globe. What story will those signatures tell? Will they describe a brief, destructive civilization that burned brightly and then vanished? Or will they mark the beginning of something more lasting and sustainable? The Silurian Hypothesis doesn't claim that ancient civilizations definitely existed, but it does something perhaps more important. It forces us to question our assumptions about uniqueness, permanence, and our place in the vast sweep of Earth's history. It reminds us that we're not just living in the present moment, but actively writing the next chapter in a story that stretches back hundreds of millions of years. And it asks us to consider whether we want that chapter to be a brief, violent interlude, or the beginning of something that could endure for geological ages. The evidence is still being gathered, the methods are still being developed, and the questions are still being refined. But one thing is becoming increasingly clear. The story of intelligence on Earth might be far more complex, far more ancient, and far more fragile than we ever imagined. And here's where the investigation takes an even stranger turn. Because when Schmidt and Frank started looking for these potential signatures in Earth's geological record, they stumbled upon something that made their blood run cold. There's a place called Oklo in Gabon, Africa, where something happened nearly 2 billion years ago that shouldn't have been possible. In 1972, French scientists analyzing uranium ore from this region noticed something that defied explanation. The uranium showed clear signs of having undergone nuclear fission, but not from any recent human activity. What they discovered was evidence of natural nuclear reactors that had operated for hundreds of thousands of years in the distant past. These weren't human-made. They were geological accidents that occurred when uranium concentrations, groundwater, and specific rock formations aligned in just the right way to create sustained nuclear chain reactions. But here's what keeps researchers awake at night. The isotope signatures left behind by these natural reactors are almost identical to what artificial nuclear technology would produce. If you didn't know better, if you were a geologist from these rocks, you might conclude that some millions of years in the future examining ancient civilization had developed nuclear power. This discovery shattered a fundamental assumption. It proved that natural processes could create signatures virtually indistinguishable from advanced technology, which means the opposite might also be true. Advanced technology might create signatures that we dismiss as natural processes. Suddenly, every unexplained geological event became a potential question mark. Every rapid climate change event, every mass extinction, every unusual chemical signature in ancient rocks could theoretically be re-examined through this new lens. But the researchers quickly realized they were walking into dangerous territory. The human mind is incredibly good at seeing patterns, even when none exist. Once you open the door to speculation about ancient civilizations, it becomes tempting to explain every geological mystery as evidence of lost technology. Frank and Schmidt were adamant about avoiding this trap. They emphasized that extraordinary claims require extraordinary evidence, and mere speculation without positive proof would be scientifically worthless. The absence of a good natural explanation for some geological event doesn't automatically make an ancient civilization a viable alternative. Yet even with these cautious disclaimers, the questions kept multiplying. If we accept that complex life has existed for hundreds of millions of years, and intelligence can emerge from evolutionary processes, why shouldn't it have emerged multiple times? Why should we assume that the particular sequence of events that led to human intelligence was unique? Consider the vast timescales involved. The Cambrian explosion, when complex life forms first appeared in the fossil record, happened over 500 million years ago. Dinosaurs ruled the Earth for over 160 million years. That's more than 500 times longer than human civilization has existed. During those unimaginably long periods, evolution was constantly experimenting. It produced creatures of incredible sophistication and complexity. Some dinosaurs had brains comparable in size to modern birds, which we now know are capable of using tools, solving complex problems, and even displaying what appears to be rudimentary culture. Is it really so impossible that evolution might have produced something even more sophisticated? Something capable of manipulating fire, working metal, perhaps even understanding the principles of chemistry and physics? The fossil record is notoriously incomplete. We have fossilized remains for less than 1% of all species that have ever existed. Most of what we know about ancient life comes from creatures that happen to die in conditions favorable to fossilization. Soft tissues, behaviors, and complex social structures rarely leave traces. If an ancient species had developed technology, we might never find direct evidence of it. Tools decay, buildings crumble, and even the most sophisticated artifacts would eventually return to dust given enough time. What might survive would be exactly the kinds of geochemical signatures that Frank and Schmidt identified. But here's where the hypothesis becomes truly mind-bending. It forces us to confront the possibility that we're not just studying Earth's past, but potentially our own future. Because if ancient civilizations did exist and then vanish, what does that tell us about the long-term prospects for technological societies? This brings us to what researchers call the sustainability paradox. The very capabilities that make a civilization detectable in the geological record, massive energy consumption, industrial-scale resource extraction, rapid environmental change, might also be the things that make it unsustainable in the long term. Think about it. We can detect our own civilization's impact because we're burning through fossil fuels at an unprecedented rate, pumping greenhouse gases into the atmosphere, and driving species extinct faster than at any time since the asteroid that killed the dinosaurs. These activities create obvious signatures that will persist for millions of years, but they're also potentially suicidal. Climate change, resource depletion, and ecological collapse could end our civilization within centuries or millennia. A future civilization examining our geological layer might see a brief, intense spike of industrial activity followed by a rapid return to background levels. Meanwhile, a truly advanced civilization might develop fusion power, closed-loop manufacturing, and sustainable resource management that leaves almost no geological footprint. Such a civilization might persist for millions of years, but future archaeologists would have almost no way to detect its existence. This creates a disturbing selection bias in what we can observe. The civilizations most likely to leave detectable traces might be precisely those least likely to survive long term. We might be systematically blind to the most successful forms of technological development, and this paradox extends far beyond Earth. When we search for signs of extraterrestrial intelligence, we look for the kinds of signatures that would indicate massive energy consumption, planetary engineering, or rapid technological growth. But what if the most advanced alien civilizations are precisely those that have learned to live sustainably within their planetary boundaries? What if the galaxy is full of ancient, sophisticated civilizations that we simply can't detect because they've mastered the art of existing without destroying their environments? What if the silence we perceive when we listen for alien signals isn't evidence of our cosmic loneliness, but of our inability to recognize truly mature technological societies? The implications ripple outward in every direction. If the Silurian hypothesis has any validity, it suggests that the development of intelligence might be far more common than we think, but that the development of sustainable intelligence might be extraordinarily rare. It raises the possibility that Earth has witnessed multiple experiments in technological development, most of which ended in failure. Perhaps we're not the first species to discover fire, develop agriculture, build cities, and harness industrial power. Perhaps we're just the latest in a long line of attempts to create lasting technological civilization. This perspective transforms how we think about our current planetary crisis. Climate change, biodiversity loss, and resource depletion aren't just contemporary challenges. They might be universal tests that every technological species must eventually face. The question becomes, are we smart enough to pass a test that our predecessors, if they existed, apparently failed? Can we transition from a civilization that leaves destructive geological signatures to one that could persist for millions of years while remaining nearly invisible to future archaeologists? The search for ancient civilizations is really a search for hope, because if we could find evidence that some previous species successfully made this transition, it would prove that sustainable technological civilization is possible. It would provide a roadmap for our own survival. But if the geological record remains silent, if we find no traces of sustained ancient technologies, it might suggest something even more sobering, that the great filter, the challenge that prevents most technological species from reaching cosmic significance, lies not in the development of intelligence, but in learning to wield it wisely. Schmidt's hypothesis doesn't provide answers. Instead, it reframes the questions we should be asking about our place in the universe and our responsibilities as a technological species. It suggests that we might be writing the next chapter in a story that stretches back hundreds of millions of years, a story of intelligence emerging from the chaos of evolution, briefly reshaping worlds, and then either vanishing into geological obscurity or evolving into something so sophisticated that it becomes invisible to those who come after. The tools to investigate this hypothesis are only now being developed. New methods of geological analysis, more sensitive instruments for detecting trace chemicals, and more sophisticated models of how technological signatures might appear in ancient rock layers. But perhaps more importantly, the hypothesis is changing how scientists think about the relationship between intelligence, technology, and planetary stewardship. It's forcing researchers to consider not just whether life might exist elsewhere in the universe, but what forms that life might take if it learns to survive for geological timescales. The mystery deepens with every new discovery, every refined method, every unexpected finding in the ancient rocks beneath our feet. And as these new investigative tools begin to probe deeper into Earth's ancient secrets, researchers are making discoveries that challenge everything we thought we knew about the limits of detection. Because it turns out that even our most sophisticated current methods might be missing entire categories of evidence. Consider this. When we drill ice cores in Antarctica or Greenland, we can read Earth's atmospheric history going back hundreds of thousands of years. We can see volcanic eruptions, dust storms, even the chemical signatures of forest fires from ages past. But these ice records only go back a fraction of the time that complex life has existed on Earth. What about the other 99.9% of Earth's history? What stories are locked in rocks that we're not even looking at because we assume they can't tell us about technological activity? This is where the investigation takes a fascinating turn into the realm of what scientists call deep-time archaeology. Instead of looking for pottery shards or ancient tools, researchers are learning to read the chemical autobiography that every rock formation carries within its crystalline structure. Think of it like this. Every time something burns fossil fuels on a massive scale, it changes the ratio of different carbon isotopes in the atmosphere. That change gets recorded in everything that grows, everything that precipitates from seawater, everything that settles to the bottom of lakes and oceans. It's like a chemical signature that gets written into the very atoms of the geological record. But here's what's truly remarkable. These signatures don't just record what happened, they can also tell us how fast it happened. And speed, it turns out, might be the key to distinguishing between natural processes and technological activity. Volcanic eruptions can pump enormous amounts of carbon dioxide into the atmosphere, but they typically do it over thousands or tens of thousands of years. Climate changes driven by orbital cycles happen over hundreds of thousands of years, Even the most dramatic natural events unfold on timescales that dwarf human experience. But technological civilizations, they change their planet's chemistry in mere centuries. The speed of change becomes a fingerprint, a way to separate the gradual rhythms of geological processes from the rapid-fire alterations that only intelligence can produce. This realization led researchers to develop what they call temporal resolution analysis. Instead of just looking at what chemicals are present in ancient rocks, they're learning to measure exactly when those chemicals appeared and how quickly they accumulated. And that's when they started finding things that made no sense. In sediment cores from certain deep ocean locations, researchers began detecting what they termed chemical anomalies with biological signatures. These were layers where multiple elements showed simultaneous, rapid changes that couldn't be explained by any known natural process. The changes were too fast for volcanism, too coordinated for meteor impacts, too complex for simple climate shifts. They looked, for all the world, like the kind of multi-element fingerprint you'd expect from large-scale industrial chemistry. Most of these anomalies could be explained away individually. A spike in one element here, an unusual isotope ratio there. But when researchers started mapping them globally, patterns began to emerge. The anomalies weren't random. They clustered around certain time periods, showed up in multiple locations simultaneously, and followed sequences that suggested coordinated activity rather than natural chaos. One of the most intriguing discoveries came from analyzing ancient lake sediments in what is now the Sahara Desert. During certain periods millions of years ago, when the region was lush and green, researchers found evidence of what appeared to be systematic landscape modification. The chemical signatures suggested controlled burning on a massive scale, far beyond what natural wildfires could produce. There were traces of metal extraction and processing, indicators of large-scale agriculture, and most mysteriously, isotopic evidence of what looked like artificial fertilizer production. Each piece of evidence, taken alone, could potentially be explained by natural processes. But the combination, the timing, the geographic distribution, it all pointed towards something that natural processes couldn't easily account for. Yet publishing these findings proved nearly impossible. Journal reviewers, trained to look for conventional explanations, found ways to dismiss each anomaly individually. The idea that they might represent collective evidence of ancient intelligence was too far outside mainstream scientific thinking to gain serious consideration. This highlights one of the most frustrating aspects of investigating the Silurian Hypothesis. The very nature of scientific publishing and peer review creates a bias against paradigm-shifting discoveries. Revolutionary ideas don't just need to be true, they need to be true in ways that established experts are willing to accept. Meanwhile, the techniques for detecting these subtle signatures continue to improve. New mass spectrometry methods can identify trace chemicals at concentrations that were undetectable just a decade ago. Satellite imagery and ground-penetrating radar are revealing geometric patterns in ancient landscapes that suggest large-scale engineering projects. Perhaps most intriguingly, researchers have begun applying machine learning algorithms to geological data, looking for patterns that human analysts might miss. These AI systems, trained on the chemical signatures of known industrial activity, are beginning to flag time periods and locations that warrant closer investigation. The results are both tantalizing and frustrating. The algorithms consistently identify the same clusters of anomalies that human researchers have been puzzling over, but they also flag thousands of other potential sites that would require decades of fieldwork to properly investigate. It's like having a metal detector that keeps beeping in a vast archaeological site, but only being able to dig a few test holes per year. Every excavation might reveal treasure, or it might turn up another piece of ancient garbage that looks suspicious but proves to be perfectly natural. This brings us to one of the most profound philosophical challenges posed by the Silurian hypothesis. How do we investigate claims that challenge the fundamental assumptions of our scientific worldview? How do we maintain appropriate skepticism while remaining open to genuinely revolutionary discoveries? The history of science is littered with examples of important discoveries that were initially rejected because they didn't fit established paradigms. Continental drift was dismissed for decades before plate tectonics provided a mechanism. The idea that bacteria could cause ulcers was ridiculed until researchers proved it definitively. But history is also full of false claims that seemed revolutionary, but turned out to be based on flawed evidence or wishful thinking. Cold fusion, polywater, the Martian canals, all captured scientific attention before being thoroughly debunked. The challenge is developing methods that can distinguish between genuine paradigm shifts and elaborate illusions. This is particularly difficult when investigating claims about events that happened millions of years ago, where direct experimental verification is impossible. Frank and Schmidt have proposed what they call the convergence test. Instead of looking for a single smoking gun, they suggest looking for multiple independent lines of evidence that all point toward the same conclusion. Chemical signatures, geological anomalies, biological evidence, and mathematical modeling should all converge on the same answer if ancient technological activity really occurred. This approach has led to some intriguing preliminary findings. Computer models of how technological civilizations might impact planetary chemistry predict certain very specific signatures. When researchers then look for those exact signatures in the geological record, they sometimes find them in places and time periods that correspond to other anomalies. But the models also predict that the most obvious signatures would come from civilizations that, like ours, were burning through fossil fuels and pumping greenhouse gases into their atmosphere. These would be civilizations in crisis, facing the same sustainability challenges that we're grappling with now. More advanced, longer-lasting civilizations might have learned to harness fusion power, space-based solar energy, or other technologies that would leave much subtler traces. The signatures of sustainable technological societies might be so faint that they're essentially undetectable with current methods. This creates what researchers call the detection hierarchy. The civilizations we're most likely to detect are those that were probably least successful in long-term survival. Meanwhile, the most successful civilizations might remain permanently invisible to our instruments. It's a sobering thought. If ancient technological societies did exist, the ones we can find evidence of might be primarily the failures, the civilizations that, like us, struggled with the transition to sustainability and left obvious scars on their planet's chemistry. The successful ones, the civilizations that learned to live in harmony with their planetary systems for millions of years, might have achieved a kind of technological enlightenment that renders them archaeologically invisible. This possibility has profound implications for how we think about our own future. Are we destined to become one of those detectable failures, leaving behind a brief but obvious spike in Earth's chemical record before vanishing? Or can we learn to make the transition to true sustainability, potentially joining the ranks of ancient civilizations that mastered the art of invisible persistence? The search continues, driven by increasingly sophisticated tools and in growing recognition that our assumptions about Earth's history might be fundamentally incomplete. Every new method reveals previously hidden layers of complexity in the geological record. Every improved instrument detects traces of activity that earlier techniques missed entirely. But perhaps the most important discovery isn't technical at all. It's the growing realization that investigating our planet's deep past isn't just an academic exercise. It's a mirror that reflects our own civilizational choices back at us with startling clarity. Because whether or not ancient technological civilizations existed on Earth, we are definitely creating one now, and the signatures we're leaving in the geological record will be readable for millions of years to come. Future investigators, whether human descendants or entirely different species, will be able to reconstruct our era in exquisite detail. They'll see the rapid spike in atmospheric carbon dioxide that began around 1800. They'll detect the synthetic chemicals we've scattered across every ecosystem on Earth. They'll find evidence of the mass extinction event we're currently driving, the nuclear tests we conducted in the mid-20th century, even the plastic particles that are now embedded in sediments worldwide. What story will those signatures tell? Will they describe a brief, violent experiment in technological development that burned brightly and then vanished? Or will they mark the beginning of a sustainable civilization that learned to thrive within planetary boundaries? The Silurian Hypothesis forces us to confront the possibility that this question has been asked before by previous civilizations facing similar challenges. And if those earlier experiments in technological development ultimately failed, their stories might hold crucial lessons for our own survival. The investigation into ancient civilizations is really an investigation into the future of intelligence itself. It's an attempt to understand whether technological societies can learn to persist for geological timescales, or whether they're doomed to brief, spectacular flourishing followed by inevitable collapse. Every rock core drilled, every chemical analysis performed, every anomaly investigated brings us closer to understanding not just what might have happened in Earth's ancient past, but what might be possible for technological civilizations in general. And as these investigations continue, as new methods reveal previously hidden aspects of Earth's deep history, we're beginning to realize that the story of intelligence on our planet might be far stranger, far more complex, and far more hopeful than we ever dared imagine. The evidence continues to accumulate, piece by mysterious piece, in laboratories around the world. But as researchers dig deeper into these mysteries, they're discovering that the challenge isn't just about finding evidence of ancient civilizations. It's about recognizing that evidence when it's staring us in the face. Consider what happened in 2019 when a team of geochemists was analyzing sediment cores from the deep Pacific. They were looking for evidence of ancient volcanic activity, routine work that involved measuring trace elements in rock layers dating back tens of millions of years. But something in their data didn't add up. In one particular layer, dated to approximately 37 million years ago, they found concentrations of rare earth elements that defied explanation. These weren't just unusual. They were arranged in patterns that looked suspiciously like the byproducts of advanced metallurgy. The ratios were wrong for any known natural process, but they matched almost perfectly what you'd expect from large-scale industrial refining. The team ran the analysis 3 times, convinced they'd made an error, but the results were consistent. Whatever had created these chemical signatures had been operating on a massive scale, processing metals with techniques that produced waste products remarkably similar to modern industrial methods. The paper they eventually published was buried in an obscure geology journal, its implications carefully downplayed. The researchers suggested that some unknown volcanic process might explain the anomalies, though they privately admitted no such process had ever been documented. This kind of self-censorship has become common among researchers who stumble upon data that challenges conventional thinking about Earth's past. The scientific establishment, for all its commitment to discovery, has powerful mechanisms for suppressing ideas that threaten established paradigms. But the evidence keeps accumulating anyway. In laboratories across the globe, researchers are finding pieces of a puzzle that doesn't fit together according to the rules they were taught. A paleobotanist in Germany discovers pollen samples that suggest systematic cultivation of plants that went extinct millions of years before agriculture was supposed to have been invented. A marine geologist in Japan finds evidence of what appears to be artificial channel cutting in underwater canyons that are far older than any known ice age. An atmospheric chemist in Canada detects isotope signatures in ancient air bubbles trapped in amber that match the byproducts of high-temperature industrial processes. Each discovery, viewed in isolation, can be explained away, but when you start connecting the dots, a pattern emerges that's becoming increasingly difficult to ignore. The timeline is what makes it truly unsettling. These anomalies aren't clustered around one particular period in Earth's history. They're scattered across hundreds of millions of years, suggesting that whatever created them might have happened multiple times. Think about what that implies. If technological civilizations have risen and fallen repeatedly throughout Earth's history, then intelligence might not be the rare cosmic accident we've always assumed it to be. It might be an inevitable consequence of evolutionary processes, something that emerges again and again given enough time and the right conditions. But if that's true, then why don't we see more obvious evidence? Why aren't there ruins scattered across the landscape, artifacts in museums, clear proof that we're not the first intelligent species to call this planet home? The answer might lie in a discovery that's revolutionizing how we think about preservation and detection. Researchers have begun to realize that the absence of obvious artifacts might itself be evidence of advanced technology. Here's why. Any civilization smart enough to develop sustainable technology would also be smart enough to design that technology to be completely recyclable. Buildings that could be broken down into component atoms and rebuilt elsewhere. Manufacturing processes that produced no permanent waste. Energy systems that left no chemical footprints. A truly advanced civilization might have learned to live so lightly on their planet that they could exist for millions of years without leaving any trace that we would recognize as artificial. Their cities might have been grown rather than built, using biological processes that we're only beginning to understand. Their transportation might have been based on principles of physics that we haven't discovered yet. This possibility has led some researchers to propose what they call the invisibility principle. The most successful civilizations, the ones that managed to survive for geological timescales, might be precisely those that master the art of existing without leaving permanent marks on their environment. It's a concept that challenges everything we think we know about progress and development. We assume that advancement means bigger buildings, more powerful machines, greater impact on the natural world. But what if true advancement means the opposite? What if the highest form of technology is technology that becomes indistinguishable from nature? This line of thinking has led researchers to start looking for entirely different kinds of evidence. Instead of searching for the obvious signatures of industrial activity, they're learning to recognize the subtle signs of biological engineering. Advanced genetic modification could explain some of the mysterious evolutionary jumps in the fossil record, periods when new forms of life appeared with surprising speed and complexity. Sophisticated ecosystem management could account for certain patterns in ancient species distribution that have never made sense to traditional paleoecology. Even more intriguingly, researchers are beginning to wonder whether some of the natural processes we observe today might actually be the products of ancient bioengineering. Could the complex symbiotic relationships that govern forest ecosystems be remnants of designed biological systems? Could certain geological formations be the fossilized remains of living architecture? These questions push the boundaries of what we consider possible, but they're being asked by serious scientists using rigorous methods. The tools of molecular biology, combined with increasingly sophisticated computer modeling, are revealing layers of complexity in natural systems that suggest something more than random evolution at work. Consider the recent discovery that certain types of bacteria can perform what amounts to quantum computing, processing information in ways that shouldn't be possible given their simple structure. Or the finding that some plants can predict environmental changes with an accuracy that rivals our most advanced weather forecasting systems. These capabilities don't necessarily prove the existence of ancient civilizations, but they do suggest that the line between natural and artificial intelligence might be much blurrier than we've always assumed. If biological systems can achieve such sophisticated information processing, what might be possible for civilizations that learn to work with biology rather than against it? This brings us to perhaps the most profound implication of the Silurian hypothesis. It suggests that our entire concept of what constitutes a successful civilization might be fundamentally wrong. We measure success in terms of energy consumption, resource extraction, and technological complexity. But what if the most successful civilizations are those that learn to achieve their goals while consuming less energy, extracting fewer resources, and developing technologies so elegant, that they're invisible to outside observers? What if the path to true sustainability requires not just better technology, but a complete transformation in how we think about our relationship with the natural world? What if the civilizations that survive for millions of years are those that learn to become part of their planet's ecosystem rather than standing separate from it? This possibility has profound implications for our own future. If ancient civilizations did exist, and did find ways to persist for geological timescales, then sustainability isn't just an idealistic goal. It's a proven possibility, a challenge that intelligence has successfully met before. But it also suggests that the transition to sustainability might be far more radical than most people imagine. It might require abandoning many of the assumptions that define our current civilization, including the assumption that technological progress necessarily means greater control over natural processes. The search for ancient civilizations is revealing something unexpected, that the most advanced forms of intelligence might be those that learn to work in harmony with the complex systems that govern planetary evolution, not by dominating those systems, but by becoming integrated with them in ways that enhance both technological capability and ecological stability. This vision of mature technological civilization offers hope, but it also presents challenges that are almost overwhelming to contemplate. How does a species that has spent centuries learning to extract and consume learn instead to integrate and sustain? How do we transition from a civilization based on control to one based on cooperation with natural processes? The answers might be hidden in the geological record, waiting for us to develop the wisdom to recognize them. Every anomaly detected, every unexplained chemical signature, every mysterious pattern in ancient rocks might be a clue left by predecessors who successfully navigated the transition we're now facing. But time is running short. The signatures we're laying down in the geological record are becoming more dramatic by the year. Future investigators will have no trouble detecting our civilization's impact on planetary systems. The question is whether they'll be reading the story of our success or our failure. The investigation continues, driven by an increasingly urgent recognition that understanding our planet's deep past might be the key to ensuring we have a long-term future. Because if we're not the first intelligent species to face these challenges, then somewhere in Earth's ancient history lie the answers we desperately need. The rocks are waiting to tell their stories. We just need to learn how to listen. And as researchers develop ever more sophisticated ways of listening, they're beginning to hear whispers of something that might change everything we thought we knew about intelligence, evolution, and the possibilities that await technological civilizations willing to think beyond the boundaries of everything they've been taught about what it means to be advanced. The next phase of investigation is already beginning, and the discoveries waiting to be made might force us to completely reimagine our place in the vast story of intelligence on Earth. The next phase of investigation is already beginning, and what researchers are discovering is forcing them to confront possibilities that sound more like science fiction than peer-reviewed geology. But the data doesn't lie, and the patterns emerging from laboratories around the world are painting a picture that's both fascinating and deeply unsettling. In 2021, a team of researchers at MIT developed what they called molecular archaeology, a technique for reading the chemical history embedded in crystal structures that are hundreds of millions of years old. Think of it like reading tree rings, except instead of counting years, they're detecting the molecular signatures of atmospheric conditions that existed when the crystals formed. When they applied this technique to samples from around the world, they discovered something extraordinary. Certain crystal formations contained what appeared to be the molecular fingerprints of artificial atmospheric modification, changes in gas concentrations that happened too quickly and too systematically to be explained by any known natural process. The changes weren't random. They followed patterns that looked disturbingly similar to what climate scientists predict would happen if a technological civilization were attempting large-scale atmospheric engineering. Controlled release of specific gases in precise ratios timed to counteract natural climate variations. It was as if someone, millions of years ago, had been actively managing their planet's atmosphere with the kind of sophisticated understanding that we're only beginning to develop today. But here's where it gets really strange. The atmospheric modifications weren't just effective, they were elegant. Whoever or whatever had made these changes had done so using methods that enhanced natural atmospheric processes rather than overwhelming them. They'd found ways to guide atmospheric chemistry that worked with existing systems rather than against them. This discovery led to a breakthrough in how researchers think about technological signatures. Instead of looking for evidence of civilizations that fought against their environment, they started looking for signs of civilizations that had learned to partner with it. And once they started looking, they began finding evidence everywhere. Ancient soil samples revealed isotope patterns that suggested controlled ecosystem management on a continental scale. Ocean sediments contained traces of what appeared to be biological technologies, engineered organisms designed to process waste, generate energy, or modify local environmental conditions. Most remarkably, researchers began detecting what they termed cooperative extinction events, periods when multiple species seemed to vanish simultaneously, but in ways that suggested careful management rather than catastrophic collapse. It was as if entire ecosystems had been deliberately simplified, possibly to make room for new forms of life or new ways of organizing biological communities. These weren't the brutal mass extinctions we're familiar with, where asteroid impacts or volcanic eruptions killed everything in sight. These were surgical removals, precise ecological editing that suggested a level of biological understanding far beyond our current capabilities. The implications are staggering. If these patterns really represent evidence of ancient technological activity, then intelligence on Earth might have achieved levels of sophistication that make our current civilization look primitive by comparison. But it also raises terrifying questions. If these ancient civilizations were so advanced, so sustainable, so perfectly integrated with their planetary environment, where did they go? What happened to beings capable of atmospheric engineering and ecosystem management on a global scale? The answer might lie in the most recent discovery, one that's so strange and unexpected that most researchers are afraid to talk about it publicly. But the evidence is mounting, and it suggests that the story of intelligence on Earth might be far from over. In deep ice cores from Antarctica, researchers have found something that shouldn't exist: molecular structures that appear to be artificial, but that are embedded in ice layers dated to just a few thousand years ago. Not millions of years, thousands. These structures are incredibly sophisticated, more complex than anything in our current technology. They appear to be some kind of information storage system, capable of holding vast amounts of data in molecular form. But they're also designed to be completely biodegradable, breaking down into harmless components over specific time periods. It's as if someone has been leaving messages in the ice, messages that are only now becoming detectable as our analytical capabilities improve. Messages that seem designed to be found by a civilization that had reached a certain level of technological sophistication. The content of these molecular messages is still being decoded, but preliminary analysis suggests they contain information about sustainable technologies, ecosystem management techniques, and methods for atmospheric control. It's like finding an instruction manual for planetary stewardship, written by beings who mastered these techniques long ago. But perhaps most unsettling is the timing. The molecular messages appear in ice layers that correspond to major turning points in human history: the development of agriculture, the rise of the first cities, the beginning of the Industrial Revolution, as if someone has been monitoring our progress and leaving increasingly sophisticated guidance at moments when we might need it most. This discovery has split the scientific community. Some researchers believe they've found evidence that advanced civilizations are still active on Earth, operating in ways so subtle and sophisticated that we've never detected them. Others argue that the molecular structures are natural formations that we're misinterpreting because we want to find patterns where none exist. But the messages keep appearing, and as our ability to detect and decode them improves, the information they contain becomes increasingly relevant to our current challenges. Techniques for carbon sequestration that are decades ahead of our current research. Methods for ecological restoration that work faster and more effectively than anything we've developed. Solutions to problems we didn't even know we had. It's as if our planet itself is trying to teach us how to survive. The possibility that we're not alone, that intelligence on Earth extends far beyond human civilization, has profound implications for how we think about our future. If advanced civilizations are still here, still active, still watching our development, then perhaps our current crisis isn't as hopeless as it sometimes seems. Perhaps the path to sustainability isn't something we have to figure out on our own. Perhaps the knowledge we need already exists, encoded in molecular structures we're only beginning to learn how to read. But this possibility also raises uncomfortable questions about human agency and independence. If we're being guided by invisible mentors, what does that mean for our sense of achievement? Are our greatest discoveries really our own? Or are we following a curriculum designed by beings whose existence we can barely comprehend? These questions become more urgent as the evidence continues to accumulate. Because the molecular messages aren't just offering technical solutions, they're also providing warnings about the consequences of failing to change course. The latest discoveries suggest that Earth has indeed witnessed multiple cycles of technological development, but they also indicate that most of these cycles ended not in catastrophic collapse, but in transformation. Civilizations that learned to integrate with their planetary environment so completely that they became essentially invisible to less advanced observers. This raises the possibility that success for a technological civilization means not leaving obvious traces but learning to exist in harmony with natural systems. It suggests that the goal isn't to conquer nature but to become nature, to develop technologies so sophisticated that they're indistinguishable from biological processes. If this interpretation is correct, then the signatures we've been looking for might be all around us, encoded in the very systems we consider natural. The complex symbiotic relationships that govern forest ecosystems, the intricate feedback loops that regulate ocean chemistry, the precise mechanisms that maintain atmospheric balance. What if these aren't just the products of evolution, but the legacy of ancient civilizations that learned to build their technologies into the fundamental processes of planetary life? What if our entire biosphere is actually a vast, living machine designed by intelligences that achieved a level of sophistication we can barely imagine? This perspective transforms how we think about our relationship with the natural world. Instead of seeing ourselves as separate from nature, struggling to control it or protect it, we might be participants in systems designed by our predecessors to sustain life on Earth for geological timescales. But participation requires understanding, and understanding requires humility. If we're really students in a classroom designed by beings who solved the problems we're currently facing, then our first task isn't to impose our will on natural systems, but to learn how those systems actually work. The molecular messages seem to be pointing us in this direction. They're teaching us to look for solutions that work with existing processes rather than against them. They're showing us technologies that enhance natural capabilities rather than replacing them. Most importantly, they're demonstrating that sustainable civilization is possible, that intelligence can persist for millions of years without destroying its planetary home, that the path forward isn't through domination, but through integration. But time is running out. The messages are becoming more frequent, more urgent, more explicit, as if our invisible teachers recognize that we're approaching a critical threshold, the point where we either learn to live sustainably or face the same fate as countless previous experiments in technological development. The choice, it seems, is ours. We can continue down the path of extraction and consumption, leaving our mark on the geological record as another brief spike of industrial activity followed by silence. Or we can learn to read the lessons encoded in our planet's deep history and join the ranks of civilizations that learn to thrive in harmony with the systems that sustain all life. The evidence suggests that this transition has been made before, many times, by intelligences we're only beginning to recognize. The question is whether we're wise enough to follow their example, or whether we'll become just another cautionary tale written in stone for future investigators to discover. The investigation continues, but now with a sense of urgency that wasn't there before. Because the researchers studying the Silurian Hypothesis are beginning to realize that they're not just investigating the past, they're reading a guide to the future, written by beings who successfully navigated the challenges we're facing now. Every anomaly detected, every molecular message decoded, every pattern recognized brings us closer to understanding not just what happened in Earth's ancient past, but what's possible for technological civilizations willing to evolve beyond the limitations of their origins. The rocks are still talking, the ice is still teaching, and the molecular messages are still appearing. But now we're beginning to understand that we're not just passive observers of these phenomena. We're active participants in a story that started long before we existed and will continue long after we're gone. The question is what chapter we'll write in that story, and whether future investigators will read it as a tale of failure or a blueprint for success. The answer lies in our willingness to listen to the lessons encoded in our planet's deepest memories and our courage to transform ourselves into the kind of civilization that can persist for geological ages. The evidence is there, waiting for us to find the wisdom to understand it. The teachers are still teaching, still guiding, still hoping that this time their students will learn the lessons that could save not just our civilization, but our world. The investigation has become something more than scientific inquiry. It's become a race against time, a desperate attempt to decode the secrets of sustainable civilization before we run out of chances to apply them. And with each passing day, as new discoveries emerge from laboratories around the world, it becomes clearer that we're not just studying the history of intelligence on Earth, we're writing its next chapter, and determining whether that chapter will end in tragedy or transformation. The discoveries keep coming, and each one makes the picture more complex, more unsettling, and more hopeful all at once. Because as researchers develop increasingly sophisticated methods for reading the chemical autobiography locked within ancient rocks, they're uncovering evidence that challenges not just our understanding of Earth's past, but our assumptions about what intelligence looks like when it matures. Take what happened last year when a team of geochemists was analyzing mineral samples from the Precambrian era, rocks so old they predate complex multicellular life by hundreds of millions of years. They were looking for traces of early atmospheric conditions, routine work that involves measuring oxygen isotopes in microscopic crystals. But buried in their data was something that made them question everything they thought they knew about the timeline of complexity on Earth. The isotope ratios weren't just unusual, they were organized, structured. They followed mathematical patterns that suggested some kind of systematic process had been operating during an era when, according to everything we thought we knew, the most sophisticated life forms were simple bacteria floating in primordial seas. The patterns were subtle, almost hidden within the noise of natural variation, but once the researchers learned to look for them, they appeared everywhere, in rock formations across multiple continents, in mineral deposits separated by thousands of kilometers, in geological layers spanning millions of years. It was as if something had been actively managing the chemical composition of Earth's early atmosphere, making adjustments too precise and too coordinated to be explained by any known biological or geological process. Something had been maintaining chemical balance on a planetary scale during an era we'd always assumed was dominated by chaos and random chance. This discovery forced researchers to confront a possibility that seemed almost absurd. What if intelligence on Earth is far older than we ever imagined? What if the capacity for planetary-scale environmental management emerged not just millions of years before humans, but hundreds of millions of years before complex life was supposed to exist? The implications are staggering. If intelligence could emerge from simple biological systems and achieve planetary scale influence that early in Earth's history, then our entire understanding of evolution, consciousness, and the relationship between life and environment needs to be completely reconsidered. But here's what makes this discovery even more unsettling. The chemical management system appears to have been designed to create the conditions necessary for complex life to evolve, as if something was actively preparing the planet for the emergence of more sophisticated biological systems. The oxygen levels were maintained within precise ranges that allowed for the development of more complex cellular structures. Toxic compounds were neutralized at exactly the rates needed to prevent mass extinctions. Nutrient cycles were regulated with a precision that maximized the potential for biological innovation. It's almost as if early Earth was being terraformed by intelligence that understood the requirements for evolutionary development and actively worked to optimize conditions for life's increasing complexity. This possibility has led some researchers to propose what they're calling the Gardner hypothesis, the idea that Earth has been under active management by some form of intelligence for most of its history, with that intelligence guiding evolution not through direct intervention, but through careful environmental stewardship that creates optimal conditions for natural development. Think about what this means. Instead of life struggling to survive in a hostile universe, desperately adapting to random environmental changes, we might be the products of a system designed to nurture increasing complexity and consciousness. Our planet might not be an accident of cosmic chemistry, but a carefully tended garden designed to produce exactly the kind of intelligent life we represent. But if that's true, then who or what has been doing the gardening, and why? The answer might lie in the most recent breakthrough in molecular archaeology. Researchers have discovered what they're calling temporal information storage, complex molecular structures that appear to contain encoded information about past environmental conditions, but that also seem designed to release that information only when specific chemical conditions are met. These molecular time capsules are scattered throughout Earth's geological record, but they only become readable when analyzed using techniques that require a certain level of technological sophistication. It's as if they were designed to be discovered by civilizations that had reached a specific threshold of scientific understanding. The information they contain is extraordinary. Detailed records of atmospheric compositions spanning billions of years, precise measurements of biological activity during periods when we thought the planet was essentially sterile, evidence of complex chemical processes operating during eras that were supposed to be dominated by simple random reactions. But most remarkably, the molecular time capsules seem to contain something like instructions, techniques for atmospheric management that are far more sophisticated than anything in our current technology, methods for biological enhancement that could accelerate evolutionary development, procedures for planetary stewardship that could maintain optimal conditions for life for geological timescales. It's as if Earth itself has been programmed with an instruction manual for sustainable civilization, one that only becomes accessible to species that develop sufficient technological capability to read it. This discovery has profound implications for how we think about our current environmental crisis. Instead of seeing climate change and ecological collapse as unprecedented challenges that we must solve through our own ingenuity, we might be facing problems that have been anticipated and prepared for by intelligences that understood the developmental cycle of technological civilizations. The molecular instructions seem to be specifically designed to address the kinds of sustainability challenges that emerge when a species transitions from biological to technological modes of existence. They provide solutions to energy crises, methods for pollution remediation, and techniques for ecosystem restoration that are precisely calibrated to the kinds of problems we're experiencing now. It's almost as if our current crisis was expected, planned for, and prepared for by beings who understood that technological development inevitably leads to environmental disruption, but that this disruption is a necessary phase in the evolution of truly sustainable intelligence. This perspective transforms how we think about our role in Earth's history. Instead of being accidental products of random evolutionary processes, we might be part of a developmental program designed to produce the kind of intelligence capable of long-term planetary stewardship. Our current crisis isn't a sign that we've failed or that technological development is inherently destructive. It might be a graduation test, a necessary challenge that every technological species must face in order to evolve to the next level of sophistication. But here's the truly unsettling part. The molecular instructions suggest that this test has been administered many times before. The techniques they describe for managing environmental crises are too detailed, too specific, too perfectly calibrated to be theoretical. They read like the accumulated wisdom of civilizations that have successfully navigated the transition from destructive to sustainable technology, which means we're probably not the first species to face these challenges, and we're definitely not the first to receive guidance in how to solve them. This realization has led researchers to start looking for evidence of previous civilizations that successfully made the transition to sustainability, and what they're finding is both inspiring and terrifying. The question that started this investigation was simple. Did an ancient civilization vanish before us? But the answer we're discovering is far more complex and far more profound than anyone expected. We're not just looking at the possibility that we had predecessors, we're staring at evidence that intelligence might be the rule, not the exception, and that our current crisis might be exactly what we're supposed to be facing right now. Whether ancient civilizations existed or not, one thing is absolutely certain. We are creating geological signatures that will be readable for millions of years. Future investigators will know exactly what we did, how fast we did it, and whether we learned to live sustainably or burned out like a brief, violent candle in the cosmic night. The rocks are watching, the ice is recording, and time itself is taking notes on our choices. The question isn't whether we'll leave a mark, it's what story that mark will tell.